Title: Electromagnetic Induction Explained. Introduction. Scene: a classroom setting with a teacher, Mr. Johnson, standing at the front. Mr. Johnson: Good morning, class. Today, we are going to delve into the fascinating world of electromagnetic induction. Electromagnetic induction is a fundamental principle in physics that explains how electricity can be generated by the motion of magnets relative to conductive materials. Let's get started. Scene transition. Classroom whiteboard with relevant diagrams and equations. ACT 1. The basics of electromagnetic induction. Mr. Johnson: Electromagnetic induction is the process of generating an electric current by changing the magnetic field around a conductor. This principle was first discovered by Michael Faraday in the early 19th century. Scene: animated visuals showing Faraday's experiments with magnets and coils. Mr. Johnson: Voiceover. Faraday demonstrated that when a magnet moves relative to a coil of wire, or when the magnetic field around a coil changes, it induces an electric current in the wire. ACT 2. Faraday's Law. Scene: back to the classroom with Mr. Johnson explaining the Faraday's Law. Mr. Johnson: Faraday's law states that the magnitude of the induced electromotive force, EMF, in a closed loop is directly proportional to the rate of change of magnetic flux through the loop. Scene: whiteboard with the equation of Faraday's law and examples. Mr. Johnson: Voiceover. Mathematically, Faraday's law is represented as EMF equals d phi dt, where EMF is the induced electromotive force, phi is the magnetic flux, and dt is the change in time. A change in magnetic field strength or area enclosed by the coil will result in induced EMF. ACT 3. Lenz's Law. Scene: Mr. Johnson discussing Lenz's law. Mr. Johnson: Lenz's law, proposed by Heinrich Lenz, explains the direction of the induced current. It states that the direction of the induced current is such that it opposes the change that produced it. Scene: animated visuals showing the application of Lenz's law. Mr. Johnson: Voiceover. This means that if the magnetic field increases, the induced current creates a magnetic field in the opposite direction, and vice versa. It's essential to conserve energy and prevent self-destruction of the conductor. Conclusion. Scene: classroom setting with Mr. Johnson summarizing. Mr. Johnson: Electromagnetic induction is a crucial phenomenon with numerous practical applications, including generators, transformers, and induction cooktops. Understanding Faraday's and Lenz's laws allows us to harness this process to our advantage. Scene: students nodding in understanding and appreciation. Mr. Johnson: that's all for today's lesson. I hope you enjoyed learning about electromagnetic induction. Stay curious, and see you next time. Scene: students thanking Mr. Johnson and leaving the classroom, looking excited about their newfound knowledge. End of script.